This and the next tutorial, we are going to solve assignment 3. The first problem of the assignment is on the image charge, and it says if we have the xz and yz plane which are grounded, that means they are at potential 0, and we take a charge at the position charge q at the position x naught y naught, what should be the image charge for this problem if I want to solve for the potential in x, y in this region shown by red. Do we take the image charges such that the boundary condition is satisfied? If we wish to make the potential 0, we wish to make potential 0 on x z plane. You must be wondering where is z is coming from. Z is here, it is coming out of the paper. So, if I want to make the potential 0 on this x z plane, then I should be putting a minus q charge. Let me make it slightly different color. So, there is darker minus q charge at the position x naught and minus y 0. This makes potential 0 all over this plane x z plane. However, this does not make it 0 on the y z plane, that is this plane. To make it 0 on that plane, I will now put a charge minus q at minus x naught and y 0. That will make potential 0 all over this, but this then creates a potential on the x z plane again, and I got to neutralize that. To neutralize this, I take third image charge which I put at this point, which is plus q at minus x 0 y 0. Now, you will notice that the charge in pink and charge in green make the potential 0 on the y z plane, the real charge in red and green make the potential 0 on the x z plane, and minus q in purple and pink again make it 0 on the x z plane, minus q and red q, the real charge, make it 0 on the y z plane. So, all these set of charges make potential 0 at the desired boundary. So, the image charges are minus q at minus x naught y naught, and I have this is plus q at minus x naught minus y naught, minus q at x naught minus y naught, and I have minus q at minus x naught y naught. Problem number 2. A point charge is located at a distance of 7 centimeters from the center of a grounded conducting sphere of 5 centimeters. So, I have a grounded conducting sphere, that means the potential is 0 on this, and I have a charge, point charge q, which is located at a distance from the center which is larger than the center, the radius of the sphere. Let the radius be capital R, and let this distance, initial distance, be r 0 from the center. So, let me show it on the top. Let the distance from the center be r 0. Then we wish to calculate the potential of this charge q at this point. Why is there a potential? The potential is there because this q gives a negative image charge here, q prime, and that attracts it. Now, what we will do to calculate the potential is calculate the work done in taking the charge to r equal to infinity, and that work done will be equal to the potential energy at infinity minus potential energy at r naught. How do I calculate the work done? I will calculate by calculating the force on this charge. The force on this charge arises from the image charge q prime, which is equal to minus q r over r, if its distance is r. Notice that I am taking the distance to be r because I will be moving the image charge at from r naught to infinity, and q prime is at a distance which is equal to q prime is at a distance d which is equal to r square over r. Therefore, the distance between q and is equal to r minus r square over r, which is equal to r square minus r square over r. And therefore, the attractive force between the charge and the image charge, the attractive force F is going to be equal to 1 over 4 pi epsilon 0 q prime, which is q r over r times q over the distance square, which is nothing but r square minus r square square, and r square will go on top. So, this force comes out to be 1 over 4 pi epsilon 0 q square r r over r square minus r square square. So, work done in moving, this is attractive force, I will be applying a force in the opposite direction. So, work done by me in moving this charge from r naught to infinity is going to be r 0 to infinity, which is equal to q square over 4 pi epsilon 0, even this r comes out, and I have r dr over r square minus r square square r 0 to infinity. To integrate this, let us take r square minus r square to be equal to z square. So, that z dz is r dr, and I have therefore, work done is equal to q square r over 4 pi epsilon 0 integration r 0 is going to be z is going to be equal to square root of r 0 square minus r square up to infinity. I have z dz over z raised to 4. This gives me z cubed, and therefore, the work done is going to be equal to 1 over 4 pi epsilon 0 q square r integration square root of r naught square minus r square to infinity dz over z cubed, which upon integration gives me q square r over 4 pi epsilon 0 1 over 2 1 over r naught square minus r square. Now, we are given that q is equal to 8 microcoulomb, r is equal to 5 centimeters, which is nothing but 5 times 10 raised to minus 2 meters. R naught is given to be 7 centimeters, which is 7 times 10 raised to minus 2 meters, and therefore, the answer I get is work done is equal to q square, which is 64 times 10 raised to minus 12 times r, which is 5 times 10 raised to minus 2, divided by 4 pi 1 over 4 pi epsilon 0, which is going to be 9 times 10 raised to 9 divided by 2 times r square, r naught square, which is going to be 49 minus 25 times 10 raised to minus 4. So, this comes out to be 64 times 5 times 9 divided by 2 times 24 times 10 raised to, let us see, this comes out to be 10 raised to minus 4, 10 raised to 2, 10 raised to 11, 10 raised to minus 1. So, 3, 8, 3. So, which comes out to be 6.0 joules. So, what we have shown is that if I have this metallic sphere which is grounded, and if I take this charge of 8 microcoulombs from 7 centimeters to infinity, the work done, which should be equal to V at infinity, potential energy at infinity minus V at this point r 0, is equal to 6 joules. Taking V infinity to be 0, I get the answer V R 0 is equal to minus 6.0 joules, and that is the answer. Next question is, if we take a metallic sphere of radius r and it is charged by assembling n electrons on it, the total work done is. What we are going to assume in this, that when the electron comes, it is kind of the charge of n electrons is spread over the sphere, or we are going to take that this charge is spread over capital radius r. So, if I have n electrons, small n electrons, the potential they are going to give rise to is going to be 1 over 4 pi epsilon 0 n e over capital R for the metallic sphere. If I bring an extra electron now, so the work done bringing that extra electron is going to be V times E, which is going to be 1 over 4 pi epsilon 0 n E square over R. This is from going from n equal to number of electron n to n plus 1. So, the net work done, total work done, when we increase n from 0 to capital N is going to be the sum of all these individual works, 4 pi epsilon 0 n e square over r, n equal to 0 to n minus 1, which gives me 1 over 4 pi epsilon 0 n minus 1 over 2 r, and that is the answer. There is a nice interpretation to it. You see, conventionally when I charge a sphere with charge q, what we do is we do V dq, which is nothing but 1 over 4 pi epsilon 0 q over r dq, q going from 0 to capital Q, and that answer we get is 1 over 4 pi epsilon 0 q square over 2 r. So, if I could bring the electrons with the infinitesimal charge, that is not bring one electron at a time, but even break that electron into infinitesimal charge, then the net work done would have been 1 over 4 pi epsilon 0 n square E square over 2 r. However, we are not breaking up electrons, we are bringing them one electron at a time. So, I am over counting in this the energy required to assemble each electron n times. Each electron assembly would require the work of 1 over 4 pi epsilon 0 E square over 2 r, if I were to assemble each electron bit by bringing it in infinitesimal charges, and n electrons would require this much work, n times E square over 2 r 1 over 4 pi epsilon 0. This is the amount that I am over counting in calculating the energy that I am shown in the left. If I subtract this, I should get the right answer, and that is my answer. That is the interpretation of our answer. Next, question number 4. We are asking if a sphere of capital radius r has a charge density which depends on the distance from the center and is equal to rho 0 r, then what will be the energy of this charge distribution? So, I will think of assembling this charge as if I have a sphere of radius small r, and on top of it I bring a shell of thickness d r. Calculate the work done in this and let r small r vary from 0 to capital R. That is how I will calculate the energy of this charge distribution. So, if I calculate the charge in a sphere of radius r, this is going to be q, let us call it q r, is going to be equal to integration. Since this is spherically symmetric, I can write the volume element as 4 pi r prime square d r prime, and the charge density is rho 0 r prime. which then comes out to be 4 pi integration rho 0 r prime cubed d r prime 0 to r, which is equal to pi rho 0 r raised to 4. That is the charge which is contained in this sphere of radius small r. So, total charge on this big sphere is pi rho 0 capital R raised to 4. Now, due to this small sphere of small radius r, of radius small r, the charge is pi r raised to 4 rho 0, and therefore, the potential on the surface is going to be 1 over 4 pi epsilon 0 pi r raised to 4 rho 0 over r, which is nothing but 1 over 4 epsilon 0, in fact, rho 0 over 4 pi epsilon 0 r cubed. Now, if I bring in that shell of thickness dr, the work done, let us call it dw, is going to be equal to the potential Vr times 4 pi r square dr is the volume times rho 0 r, that is the density. And if I integrate this from 0 to capital R, I will get the total work done. So, this comes out to be 4 pi comes out, Vr is nothing but rho naught over 4 pi epsilon 0 integration r cubed times r square times r dr, and there is an extra rho naught coming from the charge. So, this becomes 4 pi cancels. I get rho naught square over epsilon 0 times this is r raised to 6. So, I get r raised to 7 over 7, which is rho naught square r raised to 7 over 7 epsilon 0 is the total work done. Let us express this in terms of the total charge. So, work done is rho naught r raised to 7 over 7 epsilon 0 or rho naught square, which is equal to q square over pi square r raised to 8 times r raised to 7 over 7 epsilon 0. So, this answer comes out to be, so this is nothing but q square over 7 pi square epsilon 0 r, and that is the answer. Just a correction, I am getting this extra factor of pi square here. Let me check where I get it from. This is coming from here, this pi I forgot to take in. So, there will be a pi here, 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 and therefore, there will be a pi here, there will be a pi here. So, final answer is q square over 7 pi epsilon 0 r, that is the right answer. Next, we want to calculate the energy of a charge distribution rho r, which is equal to rho 0 e raised to minus alpha r. So, this charge density looks like this. It is rho 0 at r equal to 0 and then goes exponentially down, which is rho r equals rho naught e raised to minus alpha r. The trick used will be same as in the earlier problem, that is, we will calculate V at r, multiply this by 4 pi r square rho r dr and integrate it from 0 to infinity. To calculate V r due to this charge in the region up to radius r, V r is nothing but 1 over 4 pi epsilon 0 q r over r. Q r is going to be integral rho 0 e raised to minus alpha r prime 4 pi r prime square dr prime from 0 to r. So, this is 4 pi rho 0 integral r prime square e raised to minus alpha r prime dr prime from 0 small r. I am going to use a small trick here to calculate this integral, which is, if I want to calculate 0 to r, r prime square e raised to minus alpha r prime dr prime, I can write this as the second derivative with respect to alpha of integral e raised to minus alpha r prime dr prime 0 to r. Notice that when I differentiate twice with respect to alpha, the exponential function gives me an r prime square, and therefore, this is going to be equal to d 2 by d alpha square 1 minus e raised to minus alpha r over alpha, which when differentiated gives me 2 over alpha cubed minus 2 r over alpha square e raised to minus alpha r minus r square over alpha e raised to minus alpha r minus 2 over alpha cube e raised to minus alpha r. So, that is the charge contained in the sphere up to radius r, and therefore, the potential V r is equal to 4 pi rho 0 over 4 pi epsilon 0 1 over r 2 over alpha cubed minus 2 r over alpha square e raised to minus alpha r minus r square over alpha e raised to minus alpha r minus 2 over alpha cubed e raised to minus alpha r, which is equal to, I cancel this 4 pi rho 0 over epsilon 0 1 over r, inside I have this whole thing 2 over alpha cubed minus 2 r over alpha square e raised to minus alpha r minus r square over alpha e raised to minus alpha r minus 2 over alpha cubed e raised to minus alpha r. Therefore, the work done is going to be rho 0 over epsilon 0 times integral 4 pi r square dr times the charge density, which is nothing but rho 0 e raised to minus alpha r 1 over r 2 over alpha cubed minus this whole thing. Let us cancel a few terms. This r cancels here, gives me r alone. So, I get 4 pi rho 0 square over epsilon 0 integral 0 to infinity. I will take this r inside and I get 2 over alpha cubed r e raised to minus alpha r minus 2 r square over alpha square e raised to minus 2 alpha r minus r cubed over alpha e raised to minus 2 alpha r minus 2 r over alpha cubed e raised to minus 2 alpha r dr from 0 to infinity. Now, we are going to use the result that 0 to infinity r raised to n e raised to minus alpha r dr is equal to n factorial over alpha raised to n plus 1, and that when applied to, let me write this term by term, work done is equal to 4 pi rho 0 square over epsilon 0. The first term gives me 2 over alpha cubed times it's r e raised to minus alpha r, and therefore, it is 1 over alpha square minus 2 over alpha square r square e raised to minus 2 alpha r. So, that is going to be 2 factorial divided by 2 alpha cubed. The next term is minus r cubed over alpha. So, I have minus 1 over alpha, r cubed will give me 3 factorial, which is 6 over e raised to minus 2 alpha r. So, 2 alpha raised to 4 minus the last term is 2 over alpha cubed, r again will give me 2 factorial divided by 2 alpha square, and that is going to be my answer, which is 4 pi rho 0 square over epsilon 0, 2 over alpha raised to 5 minus 1 over 2 alpha raised to 5 minus 6 over 16. So, that is 3 over 8 1 over alpha raised to 5 minus 1 over alpha raised to 5. There is a mistake here. I think I should not have this 2 here, because this was the integration of r. So, it should be 1 factorial. So, this is only 1, and therefore, this would be a factor of 2 here. Okay. So, now this term, the term here and term here give me 1 over alpha raised to 5. So, this becomes 4 pi rho 0 square over epsilon 0, 1 over alpha raised to 5 minus 3/8 alpha raised to 5, which gives me 4 pi rho 0 square times 5/8 alpha raised to 5 over epsilon 0. That is my answer. What about rho 0 in terms of the total charge? Now, total charge q is equal to integration rho 0 e raised to minus alpha r times 4 pi r square dr 0 to infinity, which is 4 pi rho 0 integration r square e raised to minus alpha r dr 0 to infinity, which is 4 pi rho 0 times 2 factorial divided by alpha cubed. So, this is 8 pi rho 0 over alpha cubed is the total charge. So, we can substitute rho 0 equals alpha cubed q over 8 pi and get the energy of the distribution to be W equals pi over epsilon 0 rho 0 square, which will be alpha raised to 6 times q square over 64 pi square times alpha raised to 5. So, that gives me the answer as 5 q square alpha divided by, let us see, 4, this becomes 16, pi cancels. So, 128 pi epsilon 0, that is the answer. That is the energy of this charge distribution.